Welcome. We're going to continue to talk about how the atom is arranged. That is how the subatomic particles in the atoms are kind of positioned, maybe managed, organized, whatever. And we're working towards understanding how electrons are placed in these atoms to get to what is called electron configuration. And so let's bring our notes up. So the first thing we want to look at is what's called orbital shells, or shells of orbitals. And what this is really getting at is if we take a look at the nucleus, which is this little dot, it has a low volume and it is highly massive. Call this the nucleus. It turns out that if you average the shape of the orbitals that are made up, average the shape of the orbitals to maybe a sphere, let's say, what you get is you observe these sort of onion-like shells that form around the nucleus, or these sort of layers. And each of these layers is called a shell. So maybe I put that in blue here. So each layer is a shell. Okay. So what we do is we sort of label each of these shells from one starting in the middle. This is the first shell, or we would call that the one shell. Coming outward from the nucleus to the next shell, we get to the second shell, then the third shell, and lastly for us, not really even for us, just lastly in terms of practicality, the fourth shell. We won't move beyond the fourth shell. Really, I don't think I ever moved beyond the fourth shell in college, and we're really going to stick only to the first, second, and on a very small occasion, we will dip into the third shell ever so slightly. Okay, so these are the shells. Now, it turns out that each shell holds orbitals. So each shell has some orbitals. And I should be careful about the use of the plural term orbitals, because if we look at this, the first shell only has an s orbital. So really, the first shell just has one orbital. Okay, so in the first shell, we just have one orbital. The other shells have more orbitals. But before I get to those other shells, I want to ask the question, how many electrons can fit? Or can reside in the first shell? And the answer is 2. 2 electrons total can fit into the first shell. And the reason why is because it only has one orbital. And I don't care what type of orbital it is. It's an s orbital, just to be clear. But every single orbital can only hold 2 electrons. And as we discussed previously, some of those orbitals can be made up of a few versions of the same orbital with the same energy. So it looks like, for example, the p orbitals can hold 6 electrons. In reality, p orbitals actually exist as 3 suborbitals, px, py, and pz, and each of those can only hold 2. So while it looks like it can hold 6, there are 3 suborbitals, each holding 2, giving it the appearance of 6. So just seeing this, the first shell can hold 2 electrons because it only has one orbital. And we call this, and I'll just stick with this for now, an s orbital, just to remind us. I about named it as the 1s orbital, but let's save that for a second. Turning the page, what about the second shell? The second shell has an s and 3 p orbitals. The 3 p orbitals are px, py, and pz. Make my X a little bit more clear. Okay, so we have px, py, and pz in addition to an s orbital in the second shell. Turns out that every shell has at least an s orbital. And we're going to take steps up where the second shell has s and p orbitals. The p orbitals that exist are those three suborbitals, px, py, and pz. And then the third shell is going to step even further. It has an S3, and I'm going to put an X here, like multiplying, X 3 times p orbitals and 5 times d orbitals. I'm going to leave a little space in my notes between the third and the second shell. I want to come back to determining how many electrons these shells can hold. So going to the fourth shell, we have S 3 times P. Similarly to the third shell, 5 times D and 7 times F. Okay, so let's figure out how many electrons we can hold in total in each of these shells. So if we look, we've got 4, I'm going to make this in blue, 4 orbitals total in the second shell, right? In S and 3p, that's 4 orbitals total, where 4 times 2 equals 8 electrons total can be held in the second shell. The third shell, what we can do is we can kind of count. We've got an s orbital, we've got a p orbital, 3 p orbitals, and we've got 5 d orbitals. That's going to equal, looks like 9 orbitals total. So with 9 orbitals in the third shell, what we can do is we can take 9 times 2. Why? Because we have 2 electrons in each of these shells, and that's going to equal to 18 electrons total. In the fourth shell, what we have is the opportunity to have an S, which is 1, 3 p orbitals, 5 d orbitals, and 7 f orbitals. It's the answer before, which was 9, plus 7 is 16. So 16 orbitals we can hold all the way up to 32 electrons in the fourth shell of orbitals surrounding an atom. Okay, so what we can do is we can actually name these orbitals. So each orbital in an atom is named based on its shell and orbital type. So based on its shell and orbital type, we will actually be able to name each of these orbitals. So for example, the first orbital, let's do this. The first shell has ... the 1s orbital. The 1s orbital, and it holds 2 electrons. The second shell has a 2s orbital, okay? We have another s orbital, but it's in a different shell. To differentiate it from that orbital in the first shell, we're going to call it the 2s orbital. And now we have 2p orbitals. We have 3 2p orbitals. Now, we shouldn't just say there's a 2p orbital. That's incorrect. Rather, there's a 2px, a 2py, and a 2pz. And we looked at this last time, how the p orbital actually exists as suborbitals that are parallel to one of the axes in a traditional Cartesian plane. Now, the mathematics gets a little bit more difficult into the third shell, and the axes are a little bit more cumbersome to consider for the d orbitals, but we could say we've got a 3s orbital, a 3px, a 3py, a 3pz, and then 3d, and there's actually 5 of them. And I don't want to put them in our notes as something to worry about, but we have like the 3dz squared, the 3dxy, the 3D x squared minus y squared, things like this, beyond the scope of the class. I just want to mention we have 5 of these d orbitals in the 3rd shell. Similarly, we have 5 of these d orbitals in the 4th shell. But we don't need to worry about these. These are beyond the scope of the class. They're a little bit more cumbersome to name. You can learn all about them if you take more advanced inorganic courses. Okay, so what we've done in this shorter video is we've looked at the shells around an atom, the orbital shells around an atom, and we looked at the types of orbitals that can exist in each of them. The things that we need to know is we need to be able to recognize when we're in a certain shell and know what types of orbitals are present and have a really good understanding, at least for the first 2 shells, how many electrons can reside in each of the first 2 shells. So again, take home message, you need to know how many electrons can fit into the 1st and 2nd shell. You need to know what orbital types are in the 1st and 2nd shell and be able to name the orbitals in the 1st and 2nd shell.